Hello again. We are going to begin talking about modeling behavior based on the functions that we've learned. So let's talk about those functions, and we're going to begin by talking about the parent functions in each of those families. So we've talked about three so far, and we've talked about the different forms of writing those equations, and we've also talked about the shape of the graph. So let's review all three. The first one we talked about was linear functions. We spent a lot of time on that. And there were three forms. The first form was slope-intercept, and that's y equals mx plus b. The second form was standard, ax plus by equals c. And the last form is point-slope form, which is y minus y1 equals m times x minus x1. The shape of that is going to be some kind of line. It can go up and to the right, it can go down and to the right, it can be horizontal, or it can be vertical. The second type of function we talked about was a quadratic function, and there were three forms of that as well. The first was standard, y equals ax squared plus bx plus c. The second form is vertex form, which is y equals a times x minus h squared plus k. And the last form is root form, which is y equals a times x minus r1 times x minus r2, where r1 and r2 are the roots. And the shape of that is going to be a parabola. It can either open up or it can open down. And the last type of function that we talked about was exponential functions, and those are the three forms there. The standard form is y equals a times b to the x. If you want to talk about growth, then you would use y equals a times 1 plus r to the x. And if you wanted to talk about exponential decay, you would use y equals a times 1 minus r to the x. And the form of that function is any kind of graph that levels off at a horizontal asymptote on one end and goes off to either positive or negative infinity on the other end. So those are the three types of families. All right, so if you want to know which type of function that you're dealing with, one way to look at it is, or one way to figure that out is to look at successive differences. In other words, look at the y values and how they're changing as your x's go up by ones. Okay, so if all of those successive differences are equal after just looking at one iteration, then the function is linear. So just looking at that top table, I notice that as I go from 4 to 7, that's a change of plus 3. As I go from 7 to 10, that's also a change of plus 3. And all of these changes are a change of plus 3. Each number gets higher by exactly 3. So I know that the table at the very top is going to be the table of a linear function. Okay? If the successive differences are equal after 2 iterations, then the function would be considered quadratic. So looking at the second table, if I go from 35 to 15, that's a change down by 20. 15 to negative 1 is a negative change of 16. And then I found all the other changes as well, but they're all different, so I can't say that this is linear. But now let's look at the change in those red numbers that I've written down. The change from negative 20 to negative 16 is a change of plus 4. And then from negative 16 to negative 12 is also plus 4. And in fact, all of these changes of changes are plus 4. So I can say that this second table is a table of a quadratic function. All right? And then if neither of these work, it could be worse, but it's definitely not linear or quadratic. So what I can do instead is look at successive ratios. And instead of subtracting to see the difference between the y's, I'm going to divide to see the quotient. So if I'm looking at the y's in this table, I'm not looking at what I would add to 1 in order to get 2. I'm looking at what I would multiply 1 by to get 2. Okay? So if I multiply 1 by 2, I get 2. If I multiply 2 by 2, I get 4. If I multiply 4 by 2, I get 8. If I multiply 8 by 2, I get 16. And 16 times 2 is 32. So all of those ratios are equal. So I can say that this function is exponential. All right. Now let's review some transformations that we talked about with each of the three functions that we discussed. And we will look at how the parent function changes. So the linear parent function is y equals x. The quadratic parent function is y equals x squared. And the exponential parent function is y equals b to the x. So let's look at how they change if I do any kind of transformation. First, if I move the function up 2, then the linear function has a plus 2 added to the end of it. The quadratic has a plus 2 added to the end of it, and the exponential has a plus 2 added to the very end of the function. So that's how you deal with a translation up by a certain number of spaces. The same thing with translating down a certain number of spaces. The only difference is that instead of adding that number to the end of the function, now you're subtracting that number from the end of the parent function. All right, if I want to move left or right, that's a little bit different because now the change happens to just the x part of that function. With linear, what I'm going to do, since I'm moving right 4, remember things are a little bit different when you move left and right. It's the opposite of what you would think it is. So when I'm moving right 4, I'm going to subtract 4 from just the x part. And it looks a lot like I'm moving the function down 4, but actually moving it right 4 and down 4, if you're talking about y equals x, you actually end up in the same place. So there's really not that much difference when you're dealing with linears. When you're dealing with quadratics, however, there is a bit of a change because remember, if I'm moving right 4, I have to subtract 4 from just the x part. So the quadratic looks a little bit different. That x minus 4 is going to be in parentheses and the whole thing is going to be squared. With exponentials, again, if I'm moving right 4, I subtract 4 from just the x part. So the exponent becomes x minus 4, and that is all of that is the exponent of your base b, whatever that happens to be. Okay. Similarly, if I'm moving left 5, instead of subtracting an amount, since I'm moving left, I'm going to add whatever that amount is. So this becomes y equals x plus 5. For quadratics, x plus 5 goes in the parentheses, and for exponentials, x plus 5 goes in the exponent. All right, now let's talk about stretching. When you're stretching a function, you're simply going to multiply the entire function by whatever the stretch is. So if I'm stretching by 6, then y equals x becomes y equals 6x. For the quadratic, y equals x squared becomes y equals 6x squared. And for the exponential, y equals b to the x becomes y equals 6b to the x. And the same thing if I'm compressing, it doesn't look any different. The way you know that you're compressing instead of stretching is that you're multiplying by a number that's between 0 and 1. So like 0.1, that's between 0 and 1. So I know that these will be compressions instead of stretches. And if you want to reflect around the x-axis, then what you would do is you would simply take the parent function and make it negative. So y equals x will become y equals negative x. Y equals x squared will become y equals negative x squared, and y equals b to the x will become y equals negative b to the x. All right? And if I want to reflect it around the y-axis, then just like moving left or right, the change is only going to happen to the x part of the function. Well, with a linear function, that's going to look exactly the same because if you reflect it over the x-axis, it's going to look exactly the same as if you reflected it over the y-axis, and we can talk about that more in class. But with quadratics, the negative x is going to have to go in parentheses, and with exponentials, the negative x is going to have to be the exponent. So that's a summary of all of the transformations that we will be looking at for all 3 of those functions. All right, so here's one big example. If we had y equals 4 to the x, and we changed it to y equals negative 0.3 times 4 to the x minus 2 plus 9. What transformations took place? Well, let's go through them one at a time. The negative in front, because that didn't just happen to the x, that was out in front of the entire function, that was a reflection over the x-axis. The 0.3 meant that there was a vertical compression of 0.3. Because 0.3 is between 0 and 1, we know it was a compression, not a stretch. Because of the negative 2 that's kind of tacked on in the exponent there, that's a translation of 2 units to the right. And finally, the plus 9 at the end means that the entire function moved up 9 units. So that's most of the transformations that we talked about in the last slide. We're going to go over more examples in class just to get you used to the idea of this. But if you have any questions, please let me know, and I will see you tomorrow.